once again, we have this random variable of the number of coin flips, and we're going to see that as the number of coin flips gets large, calculating things about this random variable x is actually quite annoying. Remember, we have all these complicated formulas with choosing n choose k or n choose x, and if you want to add up those, it can be very complicated. But we're going to see a way to simplify the work that is actually extremely helpful and all sorts of things by approximating this nasty random variable x by something simpler. But to start with, what is this random variable called? The name of this distribution is blank. And I'll point out, I did a little switcheroo. X is a random variable. And then I said, this distribution. So remember, the random variable has a distribution, but we sometimes call them interchangeably. So the name of this distribution is, and people said, haha, ooh, this is fun because it was a type, any word you want. Uniform, it is not uniform. So uniform is what we did last week, and the uniform was the result of one dice roll. So if I said you roll an 8-sided dice and the number you get, that would have been the so-called discrete uniform. So it could be 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8, and that's the uniform. This x also could be 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8. Oh, it could also be 0. So that's one hint that something else is going on. But they are not all equally likely. So in the uniform means everything is the same. All the probabilities are the same. This one, they are not the same. They're something else. Normal is another good guess. There is the normal random variable. But the normal random variable is one of these continuous random variables that can be any value. So it's not the normal either. Yeah, these things are types of functions, right? Like the probability x is less than x, or cumulative. Those are like types of things, but I want the name of the guy. It's like, okay, it's like a guy who walks into the room and his name is Bob, right? But if I say what's on his name tag, that would be like asking for the cumulative distribution. So it's like one shape and it has various aspects, but we want the actual shape. Let's see. I don't know is great. Does not exist also great. Some people wrote out binomial distribution, and 21 people wrote out binomial. That is the correct answer. So if you said one of those things, that's very nice. Ooh, some people were guessing geometric and Poisson. This is very exciting. I don't think we've mentioned the Poisson. What could a fish have to do with this class? Well, there's another one called the Poisson. I wonder why. The only thing I can think of is maybe you put it in ChatGPT and ChatGPT got fooled. Maybe that's why they said Poisson. I don't know. Maybe they're just being fun. Okay, well, we'll never know. Okay, binomial is right. So if you said binomial, great. Binomial distribution, also correct. So very good. Okay, the parameters I told you are n equals 8 and p equals 1/2. What is the average and what is the variance? The average, 34 out of 50 people said 4. Were there any other things? Okay, some people don't know how to do it. 4 is correct. You could either remember the formula, or in this case, I think it's very easy to just do it sort of by hand. So let me. You could do it by hand in 1 second. If you can bring a board down, right? So the expected value of x, it is the expected value of did you get ahead on the first flip plus did you get ahead on the second flip plus plus h8. You flip the coin 8 times, sum of 8 things, and each one individually, you know. So you can split it up by the linearity of expectation, which is one of the most powerful tricks in all probability. So the average of 8 coin flips altogether is the same as adding up each individual average 8 times. Okay, and in this case, they are each 1/2. 1/2 plus plus 1/2. Every individual coin flip is heads half the time and tails half the time. So you're adding up a half 8 times, which is 4. This is the formula n times p, if you want to use the formula. Okay, so 4, very good. What about the variance? The variance is trickier. You gotta think a little bit harder for the variance, but not much harder. I wonder if more or less than 34 people got the variance. Let's see. Only 19 people got the variance. The variance is 2. Let's see. Did we get any other funny ones? No. Okay, great. Let's do a quick review of the variance. The variance of x. Once again, you have the variance of x. That is the variance of these things, h1 plus plus h8. And yeah, I think we talked about this. When things are independent, when RVs, random variables, are independent, the variances add. The variances add. So just like with expected values, because the coin flips, one coin does not affect the other coin, the variances add. So you get the variance of h1 plus plus the variance of h8. The variances all add together. And so you're going to get 8 times the variance of one individual coin flip. That is going to be the answer. You need to know how to calculate the variance of one individual coin flip. Maybe I won't do the full detail, but one individual coin flip, it is 1 half the time with probability 1/2, and it is 0 with probability 1/2. That is one coin flip. And so if I do minus its mean, I do h minus 1/2, that is either plus 1/2 or minus 1/2, each with probability 1/2 with probability 1/2. And so if you do the thing squared, you do h minus 1/2 all squared, that random variable will be either be plus 1/4 or it'll be plus 1/4. So when you square it, it's always the same thing. Half the time it's plus 1/2, the other half the time it's also plus 1/2. Hey, that's always 1/4. So on average, what is this thing? H minus 1/2 squared is always 1/4. If it's 1/4 always, then the average is 1/4. And then so that shows the variance is 1/4. Okay, so the variance of h equals the expected value of h minus its mean all squared. Okay, this is all sort of review, so I'm going kind of quickly. But just to jog your memory on what these things are. So 8 times 1/4, which is 2. So the variance is 2. So the mean is 4, and the variance is 2. Okay, you're like, well, who cares? Why is it important that the mean is 4 and the variance is 2? But if you know the mean is 4 and the variance is 2, you can actually get a good idea of the shape of this thing, and that will be the topic of today's lecture. How do you approximate this thing? Only using the mean and the variance as the inputs. All right, that was a sort of a quick review. Let me see. Just for clarity, let me also press the reveal so there's no confusion on what the right answer was. And yes, okay, and a lot of people were stuck on this one, but that's okay. We're learning. Okay, yeah. Oh, maybe I'll say one last thing, which is there's the formula, which is n times p times 1 minus p. But yeah, once again, the formula is some formula. Why it's true is more exciting to me. Okay, questions or comments about the warm-up problem? So hopefully you have loaded the binomial random variable and the mean and the variance into your RAM, and now you're ready to receive some new instruction on approximating it, which we'll do over here from Professor Humphrey. Let's switch to the HDMI.
And I call n times p times 1 minus p npq most frequently,
NPQ.
where q is 1 minus
Yes.
p, q being the probability of a failure. Okay, so where are we? A quick look at a probability histogram for a binomial distribution, and this is one with n equals 20, okay, 20 trials, probability of a success being 0.4. Notice it's not 0.5, it's a little off of 0.5. And so the distribution's not perfectly symmetrical, but there's a couple things I want you to notice about it. One is, first of all, it does look pretty bell-shaped, would you not say? It's pretty bell-shaped. And again, it's a discrete distribution, so it's not like a nice flowing smooth curve there. So the probabilities, they come in steps for each discrete value of x. So it is bell-shaped, it is slightly asymmetric, but overall it's still pretty bell-shaped. And that leads us to this idea that could we fit a continuous distribution over there, and in fact a normal distribution being our usual model for a bell-shaped continuous distribution. Can we fit a normal curve over that would approximate reasonably well the probabilities for the binomial? Now, why would we want to do that? Well, the binomial, of course, we have to work out each of those probabilities for each value of x and add them up. And if n was very large, that could be a lot of work. It's certainly easier with a computer these days, but there's something to be said to saying can we get a good adequate approximation for our purposes with a normal distribution. So let's just review a couple things about the binomial and normal distributions. What we've already learned is that both of them can serve as models for so-called bell-shaped distributions. Normal, yes, we're very used to that one, but we saw that the binomial under quite a few general conditions or certain general conditions, they're pretty bell-shaped too. With a fundamental difference between the two being that a binomial is discrete, a normal is a continuous distribution. Discrete random variable and continuous random variable for binomial and normal, respectively. And a key thing here is that if x is a binomial random variable, for example, the probability x is less than 4, it's not equivalent to the probability that x is less than or equal to 4 because there is a real probability that x equals 4. Okay? You've got to really say this holds for any n greater than or equal to 4. Now, if x is a normal random variable, the probability x is less than 4, it is equivalent to the probability x is less than or equal to 4. Since the probability x equals 4 exactly, we're talking about 4 exactly, not a range that we round off to 4, but if we're saying 4 exactly, the probability x equals 4 exactly is 0. And again, that was an argument coming. Can we say it comes from calculus, in part, or would you have another?
Comes
way?
from the Greeks and their definition of area. Like
Their
area
definition
under a line is 0. I don't know.
Under it is.
It's weird.
That line is infinitely skinny.
Yes, I guess. Yeah, they invented the infinitely skinny line, which is
The
cool.
infinitely skinny line.
Yeah.
Yes. Okay. So both of these distributions have easy-to-use online calculators and R functions. They also have tables and that kind of thing. But now what we're going to do is see that we can use this normal distribution to approximate a binomial distribution. And let's just take a look at how we're going to go about doing this. And I will get these slides up today. Okay, so kind of think of your notes. Actually, I was just yesterday looking at some educational research that maintains that handwriting notes embeds it neurologically better than typing your notes. The brain kind of gets more engaged with writing notes and trying to reinterpret things rather than just copy things. Anyhow, writing things. But we'll get these up there and then make your own little notes on them from what you did from class, go over, say, oh, okay, that's what that was about. Okay. So the binomial distribution is a very skewed distribution for very small values of p or very large values of p. And we can sketch those out. But it turns out we can use the binomial pretty well, or the normal to approximate the binomial pretty well when n times p is greater than 5 and nq is greater than 5. Would we use it if n was equal to 12 and p was equal to 0.5? They're both np and nq are greater than 5. Unlikely for that small of an n. Again, it's what we call a rule of thumb. And, well, it probably isn't too bad in that case, but we tend to use it in situations where the n is at least fairly large. So we saw that for a binomial distribution, the mean was n times p. The variance was npq. Professor Nika reviewed that with the mathematized exercise rate at the start of the year, start of the class. And we remember that the mean and the variance are the parameters for a normal distribution. And so what we do is simply set the mean of the binomial distribution equal to the mean of a normal distribution. The variance of the binomial distribution is going to be equal to the variance of the normal distribution. Now, there is a little bit of a trick here. We're going to look at something called the correction for continuity. And this is kind of a little fiddly bit, but it's kind of a neat little fiddly bit. So let's flip to the paper for a moment. Okay, so let's just consider, you got a binomial distribution, and I'm just going to put some of those bars in there. Why do we go to debar? Well, maybe to get a drink, but nonetheless. Okay, and let's suppose that was a 5, a 6, a 7, and of course this goes down this way, and that goes up that way. Okay? And what we're going to do is we're going to approximate this distribution. Consider, this is a big bell-shaped distribution, but, it's a binomial there. And when we approximate this, let's see, what color will we use? I'll use a red. Okay? When I approximate this with a normal distribution, what I do is I put this continuous curve through here. And it kind of goes like this, and it kind of works out that it kind of approximately cuts off a corner here and puts it in there. It's not exactly correct, but it works. And so if I want, for example, the probability x is greater than or equal to 6, well, I'm not going to just go down to 6, because what I'm going to do is I'm going to end up missing all of this area here between, well, what's between that? Well, there's 5.5. There's 5.5. I don't want to miss this part of the bar. So what I'm going to say, I like this notation. I'm going to say the probability that x is greater than or equal to 6 for a binomial distribution is approximately equal to, for a normal distribution, the probability that x is greater than, not 6, 5.5.
Wait, hold on. What is x here?
It is our random variable that, well, the x originally for the binomial is the number of successes that we got in our end
the
trial.
x over here, when you write PBX,
Yep.
those are the boxes.
Yep.
And then when you write PNX, that's the line.
The x is still along this axis, but
Okay.
it's now,
I see.
instead of things being able to land exactly on 5 or 6, we have to say, well, I'm going to make this continuous, and anything greater than 5.5 approximates more accurately to what I want when I add up those boxes.
I see. So there's two things called x, because they're both on the x-axis, and one is the b, the binomial, and one is the n, the normal. And because they're approximately equal, like we saw in the little picture, the only thing that's confusing is they're both called x.
They're both
it's
called
like
x.
if you have two twins, I'm going to call my two twins x and x.
And
it's
x
very
and x.
confusing. X, come over for a haircut. Oh no, now I got two twins. This is a problem.
And would you like to use y? I don't want to use y. I don't want to use y.
I believe the way the ancient Romans named their twins was they would call one of them x and they'd call the other one anti-x. So there'd be x and anti-x. You must feel pretty bad being called anti-x your whole life.
It would be bad.
I feel like that's not great. Okay, anyway, we're getting off topic.
Okay, so we got that. So we can also then say, well, what if I wanted for the binomial? Hey, just a sec. I got my green top on my red pen and my red top on my green pen. This is very confusing. Okay, let's not have chaos break loose here. Okay, got it. If I had wanted the probability for a binomial that x was greater than 6, well, that would be the equivalent for a binomial that x is greater than or equal to 7. But the approximate probability is, I have to say, well, greater than 6. I don't want to include any of the 6 probability here. I'd have to go to 6.5, and I would take the probability Just a second. What's that extra bracket
you
doing
just
in?
drew two brackets.
Sorry, I drew an extra bracket. Let's get that one out of there.
Okay.
Yeah. The brain was doing something different than the hand was doing something different than what the brain wanted it to do. Okay, x is greater than 6.5. Okay, so notice how we made those corrections for continuity. We simply said, do I want to include a particular half bar, or do I want to exclude a half bar? Okay, do I want to include the probability of a particular bar in there, or do I want to exclude it? Okay.
Maybe you're going to get to this, but what happens if you want to do the probability x equals 6? What would that look like?
Oh, we can do that.
Is that coming up?
That's coming up.
Am I spoiling the lecture? Okay.
Oh, no, you're not spoiling it. Okay, so here's a part to think about. We'll kind of come back to this, is that when n is large, we often just ignore the correction for continuity, okay? And, well, maybe you already have an answer for that. Maybe you got a reason. What do you think might be the reason we ignore it when n gets very large? Okay, well, let's leave that one for now. Maybe you want to think about that one.
We could give them a math exercise and make them write something down.
We could do that.
Should we do that?
Let's give them a couple minutes on that one.
Okay, great.
They're dwelling on it right at the moment.
We'll open up this.
Okay.
And then in a few minutes, we'll ask you.
Okay.
Why might that be?
So going back to this one we showed you before, showed you this one before of the binomial with n equals 20, p equals 0.4. There is the normal distribution fit over it, and it is fit so it has the same mean and standard deviation of the binomial. Let's just verify the mean and the standard deviation. Maybe you've got a calculator with you there. Well, the easy part to do is n times p is 20 times 8. What did I say? Oh, sorry, not 20 times 8. 20 times 0.4 gives us a mean of 8. That was the easy part. And then the variance was NPQ. So I'm taking 20 times 0.4 times 0.6. 20 times 0.4 times 0.6. What's that come out to? About
4.8.
Pardon?
4.8.
4.8. And then you magically took the square root in your head.
Is 2.19089.
Oh, wow. He is good. He is good. It's good. Yeah, absolutely. Okay. So, yes, the standard deviation there is the square root of 4.8. Okay. So, let me just ask now before we move on. Does anybody not know why the standard deviation is 2.19? Okay. So, do write it there. You're here at class. You see, this is the magic of being at class. You can fill in extra little details that the variance was NPQ. That was 20 times 0.4 times 0.6. That was 4.8. And we took the square root of the 4.8 to get the 2.19, blah, blah.
In case it wasn't clear, I didn't actually do it in my head. It's written on the top of the slide over here. 2.19.
Oh, you faked it. Okay.
What can I say?
Okay. Just show a couple of extra cases in here. There's a binomial, you know, it's pretty skewed. Notice that almost all of the values of x which occur with reasonably high probabilities occur at the lower end of the distribution, although this is actually a distribution that is still skewed to the right.
This was on the midterm. This was the student guessing randomly. As if you have a 50 questions multiple choice, and there's a 1 in 5 chance of getting each one right. This is the number you're going to get right.
Woo!
You see, and you pass if you get more than 25.
Oh, that's not looking good, does it?
No, don't. Yeah, if you guess randomly for all of them, you're going to have a bad time.
Yeah, bad time. Okay. Again, fitting that binomial or the normal over top of the binomial. Same mean, same standard deviation that we have for the binomial. And again, you can just double check that. And, you know, if you were actually drawing this thing, you'd probably crop that right axis. And again, it just gives you a little clearer picture of what it's doing. And again, like notice that, you know, when this goes through and it cuts off a corner there, it kind of more or less matches up there, but not always perfectly. You see this one here gets clipped off here, and this one here is clearly smaller than this one. And this one here, you're missing some stuff totally. But overall, we have to just go with the idea that it's not, approximations are not perfect, okay? And then the question with an approximation is, there was really two questions. How good is the approximation? Is it sufficiently good for our purposes? Okay, how good do we need an approximation to be? So that's something that's dependent on your particular problem. So let's just work out a few probabilities for a binomial random variable with n equals 20 and p equals 0.4 using normal approximation. The probability x is greater than 7. Well, we don't actually need to work through the whole mathematics of the calculations there. There's many ways of doing this efficiently, but what we want to do is set up the problem properly. So let's think about this. Let's see. Is this a nice pen? It's okay. So we have got, again, okay, so just the notation, the little squiggle, the x is distributed as binomial with n equals 20, p equals 0.4. And, and the first one is we want to find the probability A that x is greater than 7. So we're going to use normal approximation for this. Set mu equal to n times p equals, well, we already did it, 20 times 0.4 equals 8. And, well, let's see, what will we do? Well, we'll put it, sigma squared equals npq equals 20 times 0.4 times 0.6. I hope that fits in, equals 4.8. But the real key one we want is sigma is the non-negative square root of 4.8 equals approximately 2.19. Okay, we already worked that out. And so then the thing is, we want the probability x is greater than 7. If we were to look at our diagram again, if I want the probability x is greater than 7, do I want to include the 7 bar? No, I want to exclude the 7 bar. I want to go to 7.5 and up. Okay, so this is going to be, so we will say the probability for a binomial that x is greater than 7 is approximately equal for a normal that x is greater than 7.5. Give me a nicer pen. And then that is going to be equal to, for a normal, that z is greater than 7.5 minus mu divided by sigma. That is going to be for a normal that z is greater than 7.5 minus, what did we say mu was? 8 divided by 2.19. Okay, that's going to get you a Z value, and then you can use your Z tables to find that probability. Not going to go through that because we've already been through that, but we're going to give you some to contemplate and check your own work here. Okay, so what about the probability? So I'm just going to write this is find this. Don't worry, gonna give you the answer to double check your work in a moment. Okay, so let's now do a couple more. B, probability x is greater than or equal to 7. For a binomial, this is going to be equal to the probability for a normal that x is greater than 6.5. Why is it 6.5 instead of 7.5? Because I want the area for the 7 bar, and so I have to go down to 6.5 to get that area for the 7 bar. Let's do all variance here for the probability x is less than 7. Less than 7, do I want to include the 7 bar? No, I don't want to include the 7 bar. So I have got to go down to 6.5 to exclude the 7 bar. But if I wanted to do x is less than or equal to 7, I want to include the 7 bar. So I have to go up to 7.5. Oh my goodness. The probability x equals 7. That's the one you were looking for, right?
That's the one I want to do. Yeah, yeah.
That's the one you want to do.
It's 0. The probability is 0 because when you do the normal approximation, probability of any point is 0. So the approximation is going to say 0.
But it isn't going to say 0. No. It isn't going to be, because when we have 20 trials, can we get 7 successes? Can we get exactly 7 successes? Absolutely we can. And there is a bar for the 7. And so for taking that and approximating that with a normal, you say, okay, x has got to be between 6.5 and 7.5. Okay, so we can get a non-zero probability there. Now this one, this is kind of a wild one. 3 is less than x, but it's less than or equal to 9. And so let's just think about this one for a moment and ask ourselves, what normal probability should I be looking for here? Now,
should we open this up?
Professor Nika, you have...
Yes. I have opened up on Mathematize a multiple choice question. You should have A or B or C or D as your options. And it is now open. Which one is right? We'll leave it on this slide, even though it is open Mathematize. I mean, I'll write the code on the board for people who need it. And it should be open. And we'll see what people said. Okay, take a minute and do that.
So you get near the end, let's ask the question about why the continuity of correction doesn't matter. We're zipping through things at a nice pace.
Okay, I think there's like 5 or so people who haven't answered yet. Maybe we'll give 15 more seconds, and then we will reveal here. Let's switch this over. Is it A or B or C or D? I guess maybe let's do, a little hybrid. Do one of each here so we can see what the possible answers were as well as what people said. Okay, let's stop here and let's reveal counts. Reveal counts. What do people say? Ooh, people like options C and D. Small extra boost for D. But some people like C as well. X is less than 3 and less than or equal to 9. I don't know which one is the right answer because I cannot do this problem unless I draw a picture. That's the only way I could possibly do it. I have to try to draw a picture in my head. Maybe we should just do it on paper. Tell us the answer, Professor Humphrey. How do we do this one? What's the right answer?
Okay, let's draw a picture. Draw a picture. What do I need? I need one screen that can do a picture.
Oh, yeah, we can do that. Okay, let's put this one over here. Let me actually swap.
So again, working with a picture here, the picture helps clarify things in your brain and reduces your chances of making a mistake. So let's kind of think of, there's a 2. I'm not doing the 0 and 1. I don't need that. And then there's the 3. And then there's the 4. And probably somewhere along the line, there's, what are we looking at? 9? Okay, let's just look at 8, 9, and 10. Again, you got some bars, and it doesn't matter whether we get their heights right or not. It just doesn't matter. That's not what we're trying to do. There's the 8, the 9, and the 10. And we want, for a binomial, the probability that, I gave it away already. 3 is less than x, is less than or equal to 9. So we seem to be doing pretty good at the top end because we said x is, for a normal, x is less than or equal to 9. And yes, we want to get that whole 9 bar. We want to get that whole 9 bar, so we have to go up to 9.5. Now, this one here, 3 is less than x. Do we want to get the 3 bar? We don't want the 3 bar. Okay, if we include the 3 bar, we're going to be including the probability that x equals 3, but it says x is greater than 3. 3 is less than x is greater than 3. So I have to go to 3.5. So yes, this probability is 3.5 is less than x is less than 9.5. And what answer
That was
that?
right around half the class got that. And then there's a few people also picked option C, where they had 2.5 instead of 3.5. But the correct answer is D, with 23 people got right. Very good.
So really the emphasis here, you're at class, let's emphasize this. You just got to be really careful on these things, okay? And if the little picture will often keep you from going astray. We don't want you going astray. We would love it if you would all get like 100% on your exams, right? But you got to be very careful to do that. Okay. So I'm going to put this up here. These are the probabilities that come out with, if you work them out using normal approximation, this is what you should get. Very close. Depends how you do it. If you do it with the tables, I think this is what you'll come up with. If you use R, you'll get them with a little more decimal places. So sometimes you can get a little bit of difference in the 4th decimal place. But you get that. So let's go with one more thing here. So our question is, those are the probabilities using normal approximation. Well, what would have happened if we had calculated the exact binomial probabilities? How good are these approximations? And here's what they are in the far right column in the reds. Again, I'll post these up here. So notice that, they're pretty good to about 2 decimal places there. Sometimes not exactly the same to 2 decimal places, but this gives you a reasonable sense of the quality of the approximation here with n equals 20, p equals 0.4. If n gets larger, so the approximations get better as n gets larger and as p gets closer to 0.5, okay? And why does it get better as p gets closer to 0.5? It's because the binomial becomes more and more symmetric. It's perfectly symmetric at p equals 0.5, slightly less symmetric for p's, say a little over 0.5, a little under 0.5. It becomes more and more asymmetric as p's get further from 0.5. So that then it takes us back to that one question we were wondering about.
This question, why do we often ignore the continuity correction when n is large? Why do people do such a thing? Try to brainstorm based on what we've done here with these little bars and stuff. Why this might be the case? Very interesting question. Okay, let's give everyone a couple of minutes to think. Even if you have no idea, think for a few minutes, and then I'll give you a warning when there's like 30 seconds left and you still have no idea.
Well, this should definitely be one they can collaborate with people around them.
Feel free to talk to your neighbor. What is going on when n gets bigger and bigger? That means it's okay to ignore the continuity correction. Or maybe another way to say it won't make a big difference. Why would that be? Okay, let's say 2 minutes.
This is good. We'll finish at a nice time for Marcus. Something to discuss with you. Yeah, I know it is.
Okay.
So I'm just going to say one thing to discuss right after class.
Sure.
Remind me.
Sure.
Remind me. I will leave you to answer this one.
Sure. Okay. Yeah. Okay, a couple seconds left. Make sure you get in your guess, even if you don't know. It's good to think about. I think I would guess some people have figured it out. There's something nice going on here that makes intuitive sense why this is true. So why can we ignore the continuity correction when n is large? Let's see what people said. We should get a nice word cloud. We got the warning emoji. I don't know what that means. Okay, because when approximation larger, significant, infinity, exact curve becomes large. Let's read some of these. The outliers become less and less. Yeah, this is the right kind of idea. As n increases, something interesting is happening. I don't think it has I wouldn't describe it in terms of outliers. So this may be the same way of describing something, but let's see. It appears more continuous. This is the right kind of idea as well. But why does it matter? Eventually, the amount is off by a very small amount. So somehow the error is small. This is what's the real answer. Why is it often? Why do we ignore it? We ignore it because the error is small. But why is the error small? Let's see. Did anybody say why the error is small? Yeah, down to find out. Amazing. That's why we go to class. Okay. There wouldn't be much difference between probabilities bars. They'd be very, very close to each other. This is the right kind of idea. The bars are doing something special as n gets bigger and bigger. Negligible, yes, that's what we're trying to figure out why. Too small, yes, some people have figured it out. Insignificant, they do not change. So I think people are on the right track. Let me show you with a picture. Hopefully the picture will do what I want. So remember, this is the slider with n and p, and this is the graph of the function, and the height of the bars are the probabilities. What happens as n gets bigger and bigger? And the fun thing is, in Desmos, I can animate n. So watch the bars. As n gets bigger and bigger, what happens? What is happening to these bars? So the bars, remember, are the probability. As n gets bigger and bigger, here, let's go all the way up to 1,000. Let's keep going bigger and bigger forever. Oh, that's the opposite way. Okay, there we go. We're getting bigger and bigger forever. What is going on? What is happening to the height of these bars? They are shrinking down to 0. So this is the reason the continuity correction is by correcting for half a bar. Either you include half a bar or you exclude half a bar. You're correcting by 1/2 a bar. But if the size of every individual bar is getting closer and closer to 0, then the error will also get closer and closer to 0. So the individual bars, the individual probabilities, the probability it's equal to any particular value is going down to 0. And that's why you don't need the continuity correction for super large n. All right, that's a great place to stop. And we'll see everybody on Wednesday.